starting the recording.
Wait a minute. Yeah.
Hope we can wind up today, is it? We can wind up.
Yes, sir. Yeah, it will complete
We can
within
wind
today.
up
Yeah.
today.
Okay, so I'll share something about analysis or what are the analysis we do, and its concept I'm going to tell. Okay, so okay, so after getting MD analysis output, uh, many kind of results we can get from the output files. So first is thermodynamic property. So we can analyze many thermodynamics property from the output of MD. So first one is energy. So many energies are there. Okay, so potential energy, kinetic energy, and total energy. So they are representing the system's energy. So is our molecular dynamics is proper, or is it okay? Uh, we get to know from the energy analysis. Particularly, potential energy is uh, considered mainly for that. Okay, so others are varying in system, but as we discussed earlier, energy conservation should be maintained in the MD simulation. So potential energy has to be uh, conserved throughout the MD. Uh, so we have to check the quality of our MD from potential energy. For that, no, so it is important. And uh, here in the output file we have velocity, and first step we are calculating the mass of the protein or the molecule of our interest. So they are they are enough, and other parameters are there in the output file. So they involve in the calculation of energy. And heat capacity is next thermodynamic property. So we are giving a particular temperature for MD's simulation. From that, no, we can calculate the whole heat capacity. Uh, internal energy is calculated from other calculation. So derivative of internal energy is heat capacity of the system. So it is easy to derive from energy. So we get to know heat capacity that that is that can be analyzed. And pressure, so we give particular pressure of the system, but no, so the system runs in different pressure. Okay, it won't maintain the same pressure, and it try to adjust uh, within the uh, within the simulation bar. Okay, so it has to vary, otherwise some atoms may go go out, or some uh, some atoms or molecules may collapse inside the box, so pressure has to be relaxed in the system. So we can uh, get the pressure information from kinetic energy. Kinetic energy is directly proportional to the pressure of the system, and temperature of the system. Sorry, pressure is pressure is uh, I told wrongly. That means pressure is not the kinetic energy. Pressure is not directly proportional to kinetic energy. Actually, it is temperature. So yeah, I wrongly told that. Okay, so temperature is directly proportional to kinetic energy, and pressure is the product of coordinate and its momentum. So it is directly proportional to that. If you know the position and momentum, so we can uh, we can derive the pressure of the system. Okay, so it is sum of each and every atom's momentum and position. So that gives pressure of the system. Next, next one is radial distribution function. So radial distribution function is the size of the system. So here theoretically we are trying to calculate the size of the s- system, and it tried to calculate one molecule's position with respect to other molecules position. So we are taking in our case we are taking protein for MD simulation. So with reference to solvent or with reference to any other molecule in the system, we try to calculate the size of all protein, and that uh, information is derived using partial distribution function. So that's why the radius of system or size of the protein is determined using radial distribution function. Okay, so we get to we get that information from this, and experimentally radius or size of the protein is determined from the crystal diffraction pattern. Okay, so we know, or it is we know the molecule information or crystal packing information from the diffraction pattern. So from that we can determine the size of the protein. So that is experimental size, and we, we can compare these two radius as sizes of protein. So if there is a crystal or crystal structures of your protein, you get experimental size, and if you run MD simulation, we uh, uh, we can determine the size of uh, theoretical size of the protein. Okay, so is it we can check is it matching or not. Okay, so that information we get from this one, and last one is phase. Okay, so phase uh, is conformational space. Uh, each and every molecule has its position. So it position is determined by position is determined in three dimension: x, y, and z, and each atom. as its potential. So potential is also defined in three dimension. So totally one atom will have three six uh, 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 six variables, and if your molecule is having n number of atoms, and it is phase will have 16 conformation or 16 times of confirmation it may take during the MD simulation. Okay, so for example, if you are taking few tens of molecule means I if the molecule is having few tens of atom, to determine the phase of that molecule, it takes the age of universe. Usually, protein contains more than 1,000 atoms, uh, or more than that. So you can imagine the phase of the protein. So we cannot determine, or it is impossible to uh, go through all the phase of protein molecule in theoretical calculation. That's why we apply so many constraints in our dynamics. So we reduce the conformational space into small domain. Okay, so after applying all those constraints, it it may create small subset of the phase space. So that is possible using that, and we have high computational power. Using that, we can fast up our calculation, but we cannot determine all the phase of protein molecule. So that is these are all the things we can analyze, and uh, conventional analysis are there: RMSD, RMSF, and radius of gyration. So you may be familiar with these terms. Okay, so RMSD is root mean square deviation. If you take we take two structures, uh, our interest to uh, check the difference between the two structure. So RMSD is uh, is giving the structural difference between the reference and another structure, or our interested structure. So we may restrict the number of atoms. So we can calculate RMSD for backbone or uh, whole protein. So this is our choice, because some may be interested in the backbone conformational state, so they may restrict to backbone RMSD. Or if you want whole proteins uh, changes, or even each and every backbone atoms changes also important for you. In that case, you can choose the whole protein RMSD. And RMSF is root mean square fluctuation. Uh, we try to calculate uh, proteins fluctuation uh, from first frame to last frame, and we calculate the average of each and every residue's flexibility. It's based on the domain or fold of the protein. So if it is loop, it fluctuates more, and alpha helix and beta sheet, they won't fluctuate much. But sometimes the some domains are moving during MD simulation, or in real domain movements are there. So these the overall folder structural changes can be observed by RMS F, root mean square fluctuation, and radius of gyration. It is giving the shapes change throughout the MD simulation. So we take one initial structure. For example, we are taking one globular protein. Its radius is uh, particular nanometer, and during simulation it may change drastically, or it will fluctuate within particular range, so that size of protein uh, can be determined using gyration. So they are all useful for understanding the protein's shape, conformation, and other changes, structural changes. And uh, other special calculations are there. So free energy calculation is one important calculation. So you are interested in calculating the ligands interaction or other protein partners interaction with your protein. Uh, in for that, no, so we have to determine the binding energy of ligand molecule with the receptor. Uh, free energy calculation is useful for that. So we have to take the output of MD simulation, and some other algorithms are developed by uh, few uh, few labs. Okay, so PBSA and PBSA two kind of analysis are there. So we can use those standalone or other tools for calculating free energy of our ligand and receptor. Chemical potential is also can be get through few specific analysis, and entropy we can derive from free energy, or using entropy we can calculate free energy. So these are all few properties or additional properties uh, we can analyze this from our MD output. Okay, yeah. Okay, so I think this is I want to share with you. So if you have any doubt, no, in this concept, you can ask. Otherwise, we'll go to analysis mode. So, this, Yeah, previously we completed until energy minimization. So energy minimization step was successful, and it created minimized conformation of our protein. And after that, we have to do NVT equilibration first. Okay, so we discussed the NVT equilibration. So, what is NVT equilibration and why do we need to do that? Okay, so this is the parameter file for NVT equilibration. Okay, so we are using MD integrator. It is leapfrog integrator. I already told uh, we are calling Newton's equation to calculate force, momentum, position, velocity, and other things from our input file. So that is taken care by MD integrator. And steps are important for running equilibration and MD. Okay, so here I'm giving 100 picosecond for NVT equilibration. So to run 1 picosecond of MD, it requires 500 steps. Okay, so I'm uh, giving 100 picosecond. So you multiply 100 into 500. So that is that much steps we required. Okay, so I gave 50,000 steps uh, to run for 100 picosecond. And this is time difference. Okay, so time difference is each and every 2 femtosecond. I need to save a position, velocity, and other outputs in the output file. Okay, so that is defined here. And yeah, the same thing is mentioned here. I want to save coordinate every one picosecond, and velocity of every 1 picosecond. Here energy of system at every 1 picosecond. And here log file, additionally log file will generate in the meantime. Okay, so everything is running simultaneously. We are running first time, there is no continuation, and links algorithm is applied for constraint. Okay, so uh, I told what is constraint dynamics. Okay, so uh, that is incorporated at this step. So links algorithm is used for constraint, polynomial constraint. Here all bonds are considered, and the links are here. Okay, so its accuracy is determined, and order is 4. Well, Verlet algorithm, it try to calculate, generate one grid. From that grid, it calculates non-bounded interaction and other calculations of atoms in the grid. And Coulombic interaction is calculated using partial mesh evolved method. And here we are doing temperature coupling. Okay. So NVT is temperature coupling. So we are applying one particular method, that is V rescale method. Okay, and we are taking protein atom here. So if you are using non-protein atom, then we have to define this non-protein. And others are this reference temperature is 300 Kelvin. we can change as per our interest of MD. Okay, so you you are you can change your own temperature here and periodic boundary in all the direction. And yeah, these things we have to carefully give. Okay, so if you make any mistake in this step, you will not get correct output. Okay, so again you may have to run it. So you must be aware of what you are changing, otherwise don't change any parameter. So if you know uh, I'm giving this surely, then you do it. Okay, so NVT equation, yeah. This command will generate input file for NVT run. Okay, so it takes this yeah, MDP input and EM output file is uh, taken, and it will add these parameters with this and generate this output. Okay, so everything is compiled here and it generates this. And now we have to run NVT. Okay, so if you give this, it will run NVT equilibration. It takes 10 minutes time. Okay, so actually we no need to wait for 10 minutes. So if you give this, it will uh, like energy minimization. It will give output for equilibration, NVT equilibration. Okay, so meantime, now if you have any question, you can ask. I'll try to sorry. I'll try to share the NPT parameter file meantime. Here, same thing will be there. So NPT equilibration is also for 100 picosecond, and all parameters will be same. And now you can see we are including pressure coupling. Okay, so previously we did not determine, or we didn't define any pressure for equilibration. Now we are going to use Parinello-Rahman method for pressure coupling, or applying the pressure to this system. And the type of pressure is isotropic. Okay, so it should be uniform in from all the direction. And time constant is this, and our pressure limit is 1 bar. 1 bar pressure we are applying to the box, and compressibility is this much. And it is for water, so water compressibility should maintain. Otherwise, more water molecule will go towards one direction or other, and others are same. And yeah, okay, I'll stop this. run. Okay, so okay, it didn't created a output file. I should have run. Okay, okay, it will take 10 minutes or what? Okay, so yeah, another output file is there. Means MD input parameter file is there. So I'll explain that. Uh, Here we are using uh, both pressure and temperature coupling in MD, and the time is different. Okay, so uh, I'm giving it for 100 nanosecond. 100 nanosecond is uh, 100 into 1000 picoseconds, and multiply that with 500 500, and you will get uh, these many steps for 100 nanosecond. Okay, so that I mentioned here, and all other things are same. Okay, so we no need to change anything here. And if you run uh, MD simulation for that, you get 100 nanosecond MD output. Okay, so it generates XTC, TRR, and grow files, MD grow, and energy file will come. So these three outputs will come: coordinates, velocity, and energies. And using that, no, so we have to analyze this other things. Okay. Yes, it will take more time to complete. Yes, so NVT run will go like this, and NPT also will run for 10 minutes, and most probably MD will take multiplication of this. Okay, so uh, nearly 1 day or 2 days, 2 3 days it will take for 100 nanosecond in this system. So based on the system capacity, it may run faster, or it may get delayed. Yeah, means other analysis I completed, because we cannot run MD simulation and wait for its output file. So I already did basic analysis of 100 nanosecond outputs. Okay, so I'll try to show them. So potential energy output is like this. Okay, so actually the time period is less here. It run for less time period, so it is giving that. And starting potential energy is here, and it reached from this energy to this. Okay, so it reduced to this level. So after completion of MD, we get XTC file and TPR file we generated before running MD simulation. Okay, so this command is for calculating RMSD. Okay, so RMS, it takes output files uh, from MD XTC, and another input MD file is needed. So it takes this, and we are trying to calculate the RMSD of protein. Okay, so I'll show how we calculate that. If you run this command, that's okay. So it will give like this. Okay, so there are many options. uh, what is our selection? So you want system selection is not needed. We may select protein with hydrogen. Protein without hydrogen is this, and C alpha atoms alone. So it is nearly 295 amino acid protein. So uh, we can check C alpha atoms RMSD or backbone atoms. Okay, so uh, 885 backbone atoms are there, and main chain atoms are this. So we may select one. We have to select group one for all protein atoms. Otherwise, backbone. If you are interested in that, these two are frequently using RMSD for calculation. So I'm selecting backbone. So I gave 4 as my option, and again we have to do is group for select the same group. Okay, reference is one and another one is this, and it generated RMSD output will be there. And next is RMSF. So it will do RMSF calculation from the same input files. And here it gives for all atoms. Means no. So we didn't define anything. So I'm selecting protein for RMSF. Okay. So it calculates each and every atom's RMSF. Okay. Root mean square fluctuation of each and every atom. And this step, no, I want residues RMSF means no. So I don't want each and every atom's fluctuation. I want to see the fluctuation of each and every amino acid. So for that, we have to give residue flag. Means what is our selection? Residue selection. Previously, we didn't define any selection of any selection for RMSF. So it calculated RMSF for each and every atom. Now I gave residue as my selection. So now uh, one is considered as first amino acid, and others go like this. Others are follow. Others will follow in the same way. If for this also I am going to give the protein because protein contains residues. Others will not have all the atoms. So less number of atom will be there in other options. If you select protein in that all atoms of residue uh, uh, are there, so we have to do that one. Okay, yeah, I did this. And finally, gyration will do with gyration. So so gyration is for protein. So we cannot calculate gyration for other options. So we have to, sorry, yeah, it calculated gyration for protein. ER is not there. Okay. So all thermodynamic properties will be here. So use the energy md.edr file, that is the energy file, to calculate all the thermodynamic properties. Okay, angle, proper diangle, improper diangle, LJ potential, Coulombic potential, LJSR, dispersion correlation, Coulombic SR, temperature, pressure, pressure DC, pressure, constant constraint RMSD, box size at XYZ, volume density, uh, volume and enthalpy and other things will be here. Okay, so we are going to calculate potential, that is 10. Okay, so we calculated potential of this. Okay, so these things can be calculated. Now I'll show the output files. Now this potential is for 100 nanosecond. So previous potential was energy minimized potential. So MD potential will look like this. Okay, so it is maintaining the same potential energy. So if you see the average, it is here. So average potential uh, didn't change throughout the MD simulation. So our MD is stable. Okay, it is output is reliable for further analysis. So can that can be checked here, looking looking the by looking the potential. So RMSD is this. Okay, so initial RMSD was here. So in MD, the starting structure is the reference structure. So RMSD is calculated uh, from this. Okay, so each and every frame is frames RMSD is compared with that and measured. Okay, so here it is. Uh, s- the structure of the protein is stable uh, in 5 angstrom. Okay, so it is uh, s- changing from 5 to 6 nanometer, but it's not going down or going more. So the MD simulation is stable because from here onwards uh, the RMSD is not changed or fluctuated much, so it is maintaining the same range. Okay, so RMSD is okay. So RMSD will change based on the structural changes and the interaction of inter interatomic interactions or intraatomic matter. So if you have more than one molecule, so it may change according to the interaction. So this is atom RMSF. Okay, the protein contains nearly 3,000 atoms. So each and every atom's fluctuation is shown here. Next, this is the residue fluctuation. So initial nearly 50 residues are missing in this protein. So it is 300 on average. It is it has 300 amino acid. Their fluctuation is shown here. So yeah, here no these residues before 200 to 180 or 170 residues. 170 to 200 amino acids are fluctuating more in this protein. So if you see your protein, it shows what is the region fluctuating more. Okay, so and this region, these two regions are having specific fluctuations. Others are fluctuating less than that, or they are not much significant. Okay, so radius of gyration is this much, means nearly 2 nanometer. Okay. So radius of gyration is maintained in this range. Okay, so average is 1.95 nanometer. So this protein uh, size is not changed throughout the 100 nanosecond. Okay, so it started nearly from this. Sorry, my connection got problem. So yeah, if you have any doubt or anything, you may ask. Meantime, I'll try to connect it again. Yeah. Yeah, means radius of gyration is we, yes. These are all the analysis we did. Okay, so we visualized that, and I will give the commands whatever I used. No, I will share those commands in the WhatsApp group, and you can try it on your system. Okay, so I hope that you installed Gromacs and you started running the command. Okay, so if you uh, if you remember or if you notice the command, you use it. Maybe I'll share within 1 hour something. After the session, I'll share commands. Yes. Uh,
Dr. Bharati, the session is over or we are waiting for
its
something?
analysis part is over, sir. So now the participants can ask their doubt, or if they
Yes, yes.
have something, no, I can help them.
Yes, yes, yes.
Yeah.
If you have any doubt, you can discuss with Dr. Bharati. I think there is no doubt. After this, any topic remaining or we are winding up?
No, sir. Yeah.
It's
From
over.
my part, it is over.
Okay, okay. So if you any doubt, you can ask. Otherwise, we will wind up the program. So thank you, Dr. Bharati and Dr. Princey. Both have been in this program, and you people will get the recordings today of this program, and you will get the certificates shortly. In 2 3 days, I will send you the certificates to your email ID. So thank you all for joining the program. Thank you. So hope you will be attending more programs of TAVR, and we will be conducting more diverse programs um, shortly. So thank you for participating. I hope no questions are there. So uh,